Algorithm analysis techniques and methods in today's fast-paced tech landscape. Understanding algorithm analysis is non-negotiable for developers aiming to build efficient software systems. This article explores advanced methods for evaluating algorithms, from time complexity to real-world trade-offs, empowering you to write code that scales seamlessly. The foundation of algorithmic efficiency at its core, algorithm analysis quantifies performance to identify bottlenecks and optimize computational resources effectively. A solid foundation requires mastering fundamental metrics like execution time and memory consumption, measured independently of hardware-specific factors. These abstract measurements ensure your evaluations remain universally applicable across diverse computing environments. Understanding these principles enables informed decisions when selecting between competing algorithmic approaches. Time complexity measures how runtime increases with input size, often expressed using asymptotic notation. Space complexity evaluates memory usage, distinguishing between working space and auxiliary storage needs. Asymptotic behavior focuses on worst-case scenarios rather than average cases to guarantee consistent performance guarantees. Beyond Big O, advanced time complexity metrics. While Big O notation dominates discussions about algorithm speed, complementary measures provide deeper insight into actual performance characteristics. Theta notation offers exact bounds when both upper and lower limits match precisely, providing precise characterizations of certain functions. Omega notation describes best-case behavior, useful for guaranteeing minimum performance thresholds under ideal conditions. Combined, these three asymptotic notations form a complete picture of an algorithm's potential performance ranges. Precise evaluation examples consider insertion sort's performance profile. In the worst case, it exhibits O(n) superscript 2 behavior but achieves omega(n) performance in already sorted inputs. This dual perspective reveals why benchmark testing remains essential alongside theoretical analyses. Hybrid implementations combining multiple strategies can exploit varying scenario behaviors for optimal results. Determining actual runtime behavior. Analytical methods rely on mathematical modeling to predict performance without requiring physical implementation. Hypothesizing algorithm behavior involves identifying dominant terms and ignoring constants for simplicity in most contexts. Treating multiplication as costlier than addition highlights nuances that matter in low-level optimization tasks. However, practical application demands considering coefficients for fine-grained tuning efforts. Evaluating space requirements. Memory constraints often become the limiting factor for complex applications dealing with big data volumes. Distinction between working space, used by algorithm itself, and auxiliary space, additional memory allocated, becomes critical. In-place sorting algorithms typically require less memory overhead compared to out-of-place implementations. Efficient memory management can dramatically reduce swap file activity on disk-based architectures. Cache-friendly design considerations. Data locality patterns influence actual memory access costs beyond basic space complexity calculations. Algorithms utilizing spatial locality tend to perform better due to CPU caching mechanisms. Reordering computations to maximize cache utilization often leads to noticeable performance improvements. Measuring cache misses explicitly introduces additional layers of complexity to traditional analysis models. Trade-off analysis between algorithms. Selecting the right algorithm depends heavily on context-specific considerations beyond pure theoretical guarantees. Quicksort's expected O(n) log n performance often makes it preferable to merge sort despite its worst-case behavior. In distributed computing environments, communication overhead may outweigh algorithmic efficiency gains. Machine learning practitioners balance model accuracy against prediction latency requirements daily. Fundamental trade-off categories. There exists a natural tension between time and space complexity in many algorithm design problems. Solutions sacrificing memory for faster lookup times enable significant performance wins in practice. Pre-computation strategies introduce upfront processing costs for later gains in query efficiency. Balancing these factors requires domain expertise and careful empirical validation. Practical validation through benchmarking. Theoretical predictions should always be validated empirically through rigorous benchmarking procedures. Varying dataset sizes systematically helps verify asymptotic assumptions about algorithm behavior. Careful measurement methodology prevents misleading conclusions about relative performance. Controlling environmental variables isolates algorithmic differences for accurate comparisons. Benchmarking methodology guidelines. Implementing micro-benchmarks allows measuring individual components rather than whole system performance. Warm-up periods eliminate JIT compilation effects in languages with dynamic optimizations. Statistical analysis of repeated runs establishes confidence intervals around measured values. Profiling tools reveal hotspots needing further investigation or optimization efforts. Real-world algorithm selection criteria. Industrial applications demand consideration of concrete business objectives beyond strict technical specifications. A chatbot prioritizes response latencies over absolute precision in many service-oriented deployments. Financial transaction systems emphasize security properties over raw computation speeds in mission-critical situations. IoT edge devices require lightweight algorithms operating under severe power constraints. Emerging trends influencing decisions. Growing interest in machine learning has introduced novel evaluation criteria centered on training/inference trade-offs. Distributed computing frameworks necessitate new modes of complexity analysis accounting for network delays. Quantum computing research reshapes our conceptual framework for understanding algorithmic behavior entirely. Multi-core architectures mandate rethinking parallelism and concurrency implications in traditional metrics. The art of algorithm refinement. Optimization rarely occurs through radical redesign, but rather iterative refinement of existing approaches. Leveraging known optimization techniques applied selectively yields better returns than brute force redesigns. Incremental improvements guided by profiling feedback lead to sustainable enhancements over time. Identifying bottlenecks through targeted instrumentation focuses improvement efforts effectively. Strategy development framework create baseline measurements establishing reference points for future comparisons. Perform feature attribution to isolate contributions from individual algorithmic choices. Experiment with variations to understand sensitivity to parameter changes. Document results systematically for easy regression tracking and collaboration opportunities. Education and community engagement. Fostering community-driven development enhances collective understanding of algorithm analysis challenges. Open source projects provide tangible examples demonstrating theory-to-practice connections. Collaborative coding sessions facilitate peer review and shared learning experiences. Public competitions stimulate innovation in solving complex algorithmic puzzles creatively. Nurturing technical excellence encourages junior developers to participate in code reviews to reinforce analytical skills naturally. Create interactive tutorials combining visual demonstrations with hands-on coding exercises. Develop pattern recognition capabilities through exposure to canonical solution templates. Teach debugging methodologies aligned with algorithmic reasoning patterns. Future directions in algorithm study. Rapid technological evolution continues to reshape the landscape of algorithmic research constantly. Advances in computer architecture create new dimensions for performance analysis considerations. Interdisciplinary collaborations expand possibilities for novel algorithmic paradigms emerging regularly. Ethical concerns related to algorithmic bias call for renewed attention in analysis practices now. Potential research frontiers. Investigation of quantum annealing algorithms presents intriguing challenges for traditional analysis models. Neuromorphic computing architectures inspire reconsideration of conventional performance benchmarks. Adversarial robustness assessments add security dimensions to performance characterization requirements. Sustainable computing goals prompt re-evaluation of energy consumption as part of holistic analysis perspectives. Conclusion. Algorithm analysis serves as the cornerstone upon which high-performance software systems are built sustainably over time. By integrating theoretical rigor with pragmatic validation methods, developers can make sound engineering decisions consistently. Takeaway action plan: begin applying formal analysis techniques to every algorithm you implement moving forward. Regularly validate theoretical expectations against empirical measurements through systematic benchmarking. Engage actively with the developer community to share insights and learn continuously. Stay updated on emerging technologies influencing algorithm design practices globally.